This is part 3 to the Intermolecular Forces series. And in this particular section, we are going to do some examples, following up with what we covered in the previous 2 parts. So on the slide here, you see 6 different molecules. What we're going to do is we're going to determine the intermolecular forces for those molecules. And I'm going to kind of give you an idea as to how you approach doing that. So one thing you want to make sure you have out is the periodic table, just so that way you can look at the Lewis structures, figure out which is more electronegative, and then ultimately trying to figure out whether those molecules are polar or nonpolar. That is the starting point when trying to answer this type of problem. So we're going to look at ammonia to begin with. Ammonia has a formula of NH3. If you don't know that, that is something that you ought to make sure you memorize. Ammonium is NH4 plus 1, and that's a way you can remember ammonia. Just take off a hydrogen plus 1 charge. So it is NH3. Now, drawing a Lewis structure for ammonia, we're going to have nitrogen in the middle, and we have 5 valence electrons around the nitrogen, and then we're going to have your hydrogen attached to the nitrogen with a single bond. So that is the first thing we got to do. Now the second thing we're going to do is figure out, is the molecule polar or nonpolar? Looking at your periodic table, we see that nitrogen is on the very far right hand side. It's more electronegative than the hydrogen, and so we're going to have a net pull up towards the nitrogen, which makes this molecule be polar. So right now we've got ourselves in a position where we understand that NH3 is polar. So now what we got to do is determine the type of intermolecular forces that are present. Now the one that should be most obvious is the fact that since we know it's polar, it's going to be dipole-dipole. That's the first one. And London dispersion will be the second one. London dispersion is the second one. Now, remember that there were 4 intermolecular forces. The 2 that have not been discussed are ion dipole and hydrogen bonding. Ion dipole is not an option because there are no ions present. There has to be an ion present, such as sodium plus, Cl minus, anything that has a charge that's represented as an ion. Hydrogen bonding, let's check and make sure. So what are the stipulations for hydrogen bonding? There has to be a hydrogen. It's there. And the other thing is the hydrogen has to be covalently bonded to either nitrogen, oxygen, or fluorine. That fits the bill here. So the third type, sorry about that. The third type is hydrogen bonding. So one of the questions, this is not a part of the question that I have, but I want to just follow up with this, is what is the most dominant force here? Which one is more dominant? Which one's going to dictate the physical property of ammonia? Hydrogen bond will do so, because in this case here it's a small molecule. London dispersion is out of the question. Then you have dipole-dipole and you have hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole, so therefore hydrogen bonding would be the answer to your question. So the next one is methane. All right, methane is CH4, and CH4 is going to have a Lewis structure of this. So once we draw our Lewis structure, we need to figure out if this molecule is polar or nonpolar. Well, it's symmetrical all the way around. The hydrogens are going to cancel out the electronegativity of the carbon. And so this molecule is going to be considered to be nonpolar. Now, since it's nonpolar, this makes the problem just a little bit easier. It can't be hydrogen bonding. It can't be dipole-dipole because those have to have polar compounds. This is nonpolar. So the only thing that's left here is London dispersion. The third molecule is ethanol. And ethanol has a formula of CH3 CH2OH. And so the Lewis structure is drawn straight from this formula. Alright, so there's your Lewis structure. Molecule, is it polar or nonpolar? What do you think? What's your best guess? If you said polar, then you're right. Why is it polar? Where's the oxygen found? It's on the right hand side of the molecule. So the dipole is going to be pulled towards the oxygen, which is the more electronegative element. So this molecule is polar because of this reason. Now we'll see in the future that this is true to some extent, but for now we're just going to keep it real simple and just focus on the fact that it is polar. And now the second question is, what type of intermolecular forces? Well, polar, dipole-dipole, London dispersion. Now the question is, does it have hydrogen bonding? Yes, it has hydrogen bonding because it has a hydrogen bonded to the oxygen. That is by definition hydrogen bonding. All right, last question here. What's the dominant force here? Since it's a small molecule, the London dispersion doesn't make a difference. The dipole-dipole H bond are the two that you have to pay attention to. And hydrogen bonding is a stronger force than the dipole-dipole. So hydrogen bonding is the dominating force here. All right, so these three are just some examples of how you would go about drawing the Lewis structure. It's not given to you. You have to draw a Lewis structure, figure out if it's polar or non-polar, and then that's how you determine the intermolecular forces. So we're going to look at the pictures that's on the right hand side. We're going to start with the middle one here. And the middle one has a ringed structure. It's got carbon hydrogens in the ring. And it also has the carbon. So if we look on the right hand side, it has this area here. So that we're going to look at that part first. So this is going to create some asymmetry to this molecule. And if you learn anything, if you remember, asymmetry really represents a polarity, something being polar. So this part of the molecule is polar because of that region. Now the rest of the molecule that you see here, I'm going to square that. So the rest of this is nonpolar. Now this molecule being polar and it's got two different parts to it. We can figure out the intermolecular forces based off of this. So London dispersion is going to be the first one that we write down. Then dipole-dipole, and then the H bond. And it's H bond because you have the OH group here. The dipole-dipole comes from this part, this region also. And I'm just going to shade that in there. All right. So it comes from that region. Now the London dispersion is this because it's in everything. So this molecule has these three. Now which of those three is going to be the dominant force? So this is where the trickiness comes in. So dipole-dipole is not going to be in play here. It's going to be between London dispersion and hydrogen bonding because it's still a bigger molecule. This molecule is going to be kind of split. It's going to be 50-50. I can't say that London dispersion is going to be stronger than the H bond. All right, and that's mainly because this top portion here is fairly polar in comparison to the rest of this, and that's going to allow it to dissolve into water. And that's something we'll get into in the future chapters where we talk about being able to dissolve into water or not dissolve into water, soluble or insoluble. So this is a tough question. This is one of those questions that you kind of have to pick and choose. So I would say that hydrogen bonding would be the dominant force in this, for the simple fact it's still not a very big molecule. And the right hand side has a lot going for it. And so H bond in this case is going to win out over the London dispersion force. You could argue that and say London dispersion force could be dominant over H bond. Like I said, that this is a tough one in that retrospect. So now we look at the next one here. All right, the next one has it's mostly carbon, so we have a carbon here and a carbon that's just not drawn in, and it has multiple oxygens surrounding it. All right, and these oxygens create some asymmetry. This molecule is going to be polar, and it's going to have London dispersion and dipole-dipole. Now, it's not a big molecule, so London dispersion is not going to be a dominant factor here. It's actually going to be dipole-dipole in this case. And the last one that we see down here has pretty big molecule. All of the corners that you see here are carbons, and some may have hydrogens. So let's see, 1, 2, 3. So there'd be a hydrogen coming off that. Now, this molecule, if you look around it, you can see that you have an oxygen here, you have an OH group here, you have NH group, an oxygen here, and yes, you have these CH3 groups coming off, but they're not anything that's going to make a difference. What does make a difference are the ones that I have circled. Those cause this molecule to be polar, and this molecule is very polar. So London dispersion is going to be one force, dipole-dipole will be a force, and then H bond will be a force. So this molecule is going to have all three of those. It's not going to have ion dipole because there's no ion present. Now, of these three, there's a hydrogen bonding here, there's hydrogen bonding here. That makes this one a lot easier. So hydrogen bond is your dominant force here. If we were to go back over here and look at the first one we did, we were talking about trying to figure out whether it's London dispersion or hydrogen bonding. It could go 50-50. In fact, I would say that London dispersion would be this. And I circled hydrogen bond to begin with. But either one. So this is one of those ways that either one of those could be the right answer. And that's because of the size of the structure. But the one on the right-hand side, it's very obvious that the hydrogen bonding is spread around the molecule, and that makes this hydrogen bonding being the dominant force. So I hope by going through these 6 examples, it helps you sort of better understand how we figure out the intermolecular forces and ultimately determining the dominant intermolecular force. So thanks for watching.